Your brain doesn't just react to stress, it alters its own landscape. Genetic predispositions modify stress hormone receptors, particularly the glucocorticoid receptor. Researchers at Stanford University found that these receptors can vary significantly between individuals, affecting how cortisol, the stress hormone, interacts with neurons. While popular belief suggests stress is purely psychological, it's a neurochemical reality. Receptor density in different brain regions, like the hippocampus, influences whether everyday worries escalate into chronic anxiety. This receptor variation is not conscious choice. It's biology at play, altering how your brain encodes stress from the cellular level. Inside your amygdala, the brain's emotional processing center, lies a key to understanding worry. UCLA studies reveal hyperactivation in Worriers, where neurotransmitters like glutamate flood the amygdala, prolonging the stress response. Unlike common belief that anxiety is simply a heightened state of mind, it's a physical increase in neural activity. This surge in neurotransmitters strengthens synaptic connections, making the brain more sensitive to perceived threats. Hyperactivation isn't fleeting. It's a structural change that sustains a state of alertness, impacting how you perceive daily challenges. This biological reality reshapes emotional responses. Inside your prefrontal cortex, the part of your brain responsible for decision-making and rational thought, chronic stress suppresses activity. A research team at Harvard found that elevated cortisol levels can reduce prefrontal cortex volume over time. This isn't just about feeling stressed. It's a tangible reduction in neural tissue, altering your capacity to regulate emotions and inhibit responses. While advice often suggests thinking positively, the biological mechanism at play shows that decision-making circuits are physically compromised by prolonged stress. The structural changes reveal a shift toward emotion-driven thinking. Your hippocampus, essential for memory formation, is particularly vulnerable to stress-induced changes. Contrary to the belief that stress merely fogs memory, it actively remodels neural pathways. Research from the University of Wisconsin-Madison shows that chronic cortisol exposure can reduce dendrite density in hippocampal neurons. These dendrites are the branches that connect neurons, and their reduction means fewer connections, leading to impaired memory formation. This isn't just a mental block, it's a physical alteration in brain architecture, emphasizing how stress reconfigures the very substrate of memory storage within your brain. Dopamine, the neurotransmitter often associated with pleasure, plays a surprising role in worry. Princeton researchers discovered that individuals with high anxiety levels show altered dopamine signaling in the prefrontal cortex. This isn't merely about feeling less joy. It's a downregulation of dopamine receptors, affecting motivation and reward processing. Popular psychology suggests shifting focus for happiness, but the biological mechanism indicates that receptor downregulation changes your brain's reward landscape. This neural adaptation shifts emotional responses, leaving worriers with a predisposition to interpret situations more negatively, due to chemical changes in perception. Cortisol, often dubbed the stress hormone, does more than just trigger fight-or-flight responses. It impacts the hippocampus by decreasing dendritic complexity, as seen in studies conducted at Emory University. This reduction in dendritic branches disrupts synaptic connectivity, specifically in areas responsible for learning and memory. Cortisol does not simply make you feel stressed. It structurally alters neuron architecture, affecting how information is processed and retained. The rewiring occurs at the synaptic level, causing lasting impacts on memory formation. It's not just stress, it's a molecular transformation that reshapes cognitive functions. The amygdala doesn't just react, it forms alliances with the prefrontal cortex, impacting emotional regulation. Researchers at the University of Pittsburgh found that stress enhances connectivity between these regions, leading to amplified emotional responses. This increased connectivity contradicts the notion that emotional reactions are solely psychological. Instead, it's a heightened neural circuit feedback loop that reinforces anxiety. The stronger the connection, the less control the prefrontal cortex exerts over emotional outbursts. This neurophysiological mechanism, rather than conscious choice, dictates the intensity and frequency of worry responses under stress. Dopamine receptor downregulation within the basal ganglia unveils part of the habit loop in Worriers. Studies at King's College London indicate that chronic stress leads to a decline in dopamine D2 receptors, a crucial component in regulating reward processing. This receptor downshift influences the encoding of habit loops, making worry a potentially ingrained behavior. It's not just a tendency to fret, it's a neurobiological shift making worry a default neural pathway. This alteration in reward circuitry underscores the persistent nature of anxiety and its intrusion into habitual patterns of thought and behavior. The default mode network DMN, pivotal in self-referential thought, shows heightened activity in Worriers. Neuroimaging studies from MIT reveal increased DMN connectivity during rest states in those prone to anxiety. This isn't just introspection, it's a neural predisposition towards rumination. The DMN governs internal dialogue, and in Worriers, its hyperactivity fosters a cycle of self-doubt and negative thought patterns. This isn't simply overthinking, it's a physiological state anchored in persistent neural engagement that perpetuates worry. The network's overactivity manifests as a continuous loop of anxious thought. Brain-derived neurotrophic factor, BDNF, crucial for neuroplasticity, diminishes under chronic stress, as shown in studies at Johns Hopkins University. Low BDNF levels hinder the brain's ability to adapt and form new synaptic connections. For Worriers, this means less flexibility in shifting thought patterns or emotional responses. It's not merely a feeling of being stuck, it's a molecular limitation on adaptability. Reduced BDNF expression constrains the brain's capacity for growth and change, anchoring worry in a fixed neural landscape. This biochemical shift limits cognitive adaptability and emotional resilience. Chronic stress differs fundamentally from acute stress, as each impacts your brain in distinct ways. Acute stress, a temporary state, can enhance memory and decision-making by boosting norepinephrine levels in critical brain regions. However, chronic stress leads to prolonged cortisol exposure, as demonstrated in longitudinal studies at Yale University, which shrinks the hippocampus over time. This contrast reveals that while short-term stress might refine focus and response, sustained stress degrades cognitive structures. Rather than just a state of mind, chronic stress reconfigures neural architecture, making anxiety a persistent, structural challenge. The self-help industry often promotes quick fixes for stress, yet peer-reviewed neuroscience paints a different picture. A meta-analysis from the University of Toronto highlights that genuine anxiety reduction correlates with long-term neural changes rather than immediate interventions. Neuroplasticity underlies these shifts, requiring sustained effort and environmental stimuli to rewire worry circuits. Contrary to instant calm claims, the brain's restructuring takes time, involving gradual changes in synaptic strength and connectivity. This understanding underscores the discrepancy between popular solutions and actual neurobiological processes, emphasizing the complexity of altering entrenched worry patterns. Brain imaging studies reveal significant insights that contradict popular psychology. Functional MRI scans at the University of Michigan illustrate that amygdala-prefrontal cortex communication differs markedly in Worriers. Unlike the suggestion that simply thinking positively can mitigate anxiety, these scans show reduced prefrontal cortex activity, indicating diminished regulation over the amygdala. This isn't just about mindset. It's a measurable decrease in neural control. The imaging data demonstrates structural and functional brain differences, challenging simplistic narratives and highlighting the intricate neural underpinnings of anxiety that demand deeper understanding. The long-term effects of chronic worry extend beyond emotional distress, influencing physical health through vagus nerve signaling. Research at Columbia University shows that sustained anxiety downregulates vagus nerve activity, impacting heart rate variability and stress response. This isn't merely stress-induced tension, it's a physiological alteration in how your body manages stress signals. The vagus nerve, a critical component of the parasympathetic system, becomes less effective, leading to heightened stress sensitivity. This neural adaptation underscores the systemic impact of chronic worry, linking mental states to broader health implications. A reframing fact emerges from a 2019 study at the University of California, where researchers found that worriers exhibit heightened threat detection, a trait rooted in evolutionary biology. This isn't just anxiety, it's a heightened vigilance mechanism with roots in survival. The amygdala's increased sensitivity to threats can be seen as an advantage in certain contexts. About 60% of participants showed greater responsiveness to environmental changes, suggesting that worry might protect against unforeseen dangers. This evolutionary perspective reveals how certain neural traits, while challenging, offer adaptive benefits in specific scenarios.